Hello again and welcome back. For our final two lectures, we're going to focus on the topic of differential equations. We've seen some differential equations throughout this course, but for the next two lectures, we'll focus in on them. This is a big topic in mathematics, especially in applied mathematics and engineering. We teach at the University of Florida many courses completely devoted to solving differential equations. Today I'd like to sort of talk about some fairly straightforward ideas on how you verify that a function is a solution to a differential equation, and then look at a visual representation of solutions. It's called slope fields. And at the very end of the lecture, we'll talk about an actual method for solving differential equations. In the lecture following this one, we'll be totally devoted to applications of differential equations. Let's recall now what a differential equation is. It's nothing more than an equation involving, in x and y, and involving derivatives of y. So it's an equation with some derivatives. And the idea is to find a function which satisfies that equation. If the derivative occurs to the first derivative only, then it's called a first-order differential equation. So the goal is to find solutions to differential equations. And when you find a solution, is it the only one? Have you got them all? And those can be pretty subtle questions. The applications of differential equations span all of science and engineering: fluid flow, heat transfer, motion, etc. When I was younger, I worked at NASA off and on, and we solved differential equations that modeled airplane wings and the stresses on airplane wings. I spent some time trying to solve differential equations with computers. So it's a big business, and a lot of agencies around the world devote their time of their scientists to solving differential equations. So let's not get too involved with this. Let's look at some simple examples. Suppose I give you the first order differential equation y prime plus 2y equals 0. Can we verify that ce to the minus 2x is a solution? Ce to the minus 2x. How would you verify it? Well, you would plug it into the equation. First, you'd have to know the derivative. So the derivative of ce to the minus 2x is minus 2 ce to the minus 2x. I'm differentiating e to the minus 2x by the chain rule. So the minus 2 pops out. And then I take the derivative, add it to 2 times the function, and hope to get 0. So the derivative is minus 2 ce to the minus 2x plus 2 times the function ce to the minus 2x, and lo and behold, they cancel each other, and yes, it's a solution. This is a first-order differential equation because the derivative is the first derivative. And again, a more subtle question is, are there other solutions that are not included in the one I gave you? In this example, all solutions are of the form ce to the minus 2x, where c is a constant. That includes the solution 0. 0 solves that differential equation because the derivative of 0 is 0. And that would be the constant c equal to 0. Now, that solution had that arbitrary constant, and that's a whole family of solutions, an infinite number of solutions. And for each value of c, you get a curve. And those are called solution curves. Here's a picture of some of the solution curves to that differential equation we just looked at. And you notice that the curves don't intersect each other, and they are sort of decaying exponentials for the positive portion, and then, of course, the one on the bottom is when c is a negative number. Those solution curves, you have an infinite number of solutions. If you have an initial condition, some more information, you often can pick out one of the solution curves as the answer. Let me talk about that issue of side conditions with a second-order differential equation. Here's one we've seen before, though. You might remember that with a falling body, the only force acting upon it is the force of gravity. And the gravitational constant is minus 32 feet per second squared. So the acceleration of a particle, the second derivative of the position function, is minus 32 feet per second squared. So that's a second order differential equation. S double prime equals minus 32. Well, you can solve that differential equation. Here's one way to solve it. I won't do it, but here's how you would do it. You would integrate it once to get S prime, and that would introduce an arbitrary constant. And then you would integrate it again, and you would get S, and that would have two arbitrary constants. Or I'm just going to give you the solution. I'm going to give you the solution as minus 16t squared plus c1t plus c2. You can check that I'm right. Differentiate that position function. What's the first derivative? It's minus 32t plus c1. What's the second derivative? Minus 32. You see how the two constants go away when I differentiate twice? C2 goes away when I do the first derivative, and C1 disappears when I do the second derivative. So this is a second order differential equation, and we've played with this one before. It has two arbitrary constants, but if you were given some side conditions, you could find those constants. This might look familiar from a previous lecture, but suppose you also knew that S of 0 was 80 and S prime of 0 was 64. In other words, the initial position at time 0 was 80 feet, and the initial velocity at time 0 was 64 feet per second. Well, knowing those two extra conditions, you can determine the constants C1 and C2. Here we go. Remember, the function is S of t is minus 16t squared plus C1t plus C2. Now, plug in 0 into that equation. The first two terms disappear, and you're left with C2 equal to 80, because S of 0 is 80. So now we know C2. Now take the derivative, minus 32t plus C1, and plug in 0 for t. And you get the equation that C1 is 64. So the particular solution to our problem, to this second order differential equation, is minus 16t squared plus 64t plus 80. Good. I'd like to look at another example to introduce the idea of slope fields. And so let's first look at a function and verify that it solves a certain differential equation. So the function I'm going to consider is cx cubed, and the differential equation is xy prime minus 3y equals 0. So I want to verify that cx cubed satisfies that differential equation. And then we're actually going to pick out a particular solution that when x is minus 3, y is 2. So we know how to check solutions. You take your proposed solution, cx cubed, and differentiate it. So you get 3cx squared. And now plug it into the differential equation. So xy prime minus 3y becomes x times the derivative, 3cx squared, minus 3 times the function, which is cx cubed. And notice that these cancel each other, and you're left with 0. So indeed, that is a solution. What's the particular solution? Well, we know that when x is minus 3, y is 2. So plug those values in for x and y, and you get that 2 equals c times minus 3 cubed, and if you solve that, c is minus 2 over 27. So let's summarize. Our particular solution is y equals minus 2 over 27 x cubed. Let me be clear about this solution. That function satisfies the differential equation, and it passes through the point minus 3 comma 2. It satisfies the initial condition. It's a unique function that satisfies both the differential equation and the initial condition. Good. Let me step back a minute and talk in general about differential equations. As I said, this is a big field. Solving them can be very difficult. Entire courses are devoted to it. There are many, many numerical methods for solving differential equations as well. Most graphing utilities now have built-in techniques for solving differential equations. And if you look at the booklet for your graphing calculator, you'll see a chapter on numerical methods, approximation methods for solving differential equations. The advanced placement syllabus requires a knowledge of differential equations, and in particular something called slope fields. Whereas in college, in freshman calculus, we generally don't do much with differential equations. The reason being we have a course that follows our calculus sequence completely devoted to differential equations. So let's look at slope fields for a moment. Slope fields basically are a visual, a picture of what the solutions look like without ever finding the solution. It's kind of a curiosity. I think you'll enjoy this. It's kind of, it's a little bit of art involved with this. So let's do an example and I'll show you what's going on. In that previous problem we just did, we had the differential equation xy prime minus 3y equals 0, and we can solve for y prime to get y prime equals 3y over x. So y prime is 3y over x. Now imagine you didn't know the solution to that equation. All you were given was the differential equation y prime equals 3y over x. And you don't know the solution. And you sort of tell yourself, well, I don't know how to solve that differential equation, but I can draw a picture of it. Watch what, you do know something about the solution. You know its derivative. You know y prime, don't you? You know the slope of the solution. You don't know y, but you know the slope. You know y prime. So watch what you do. You pick an x and y value, x and y, and then for that pair of xy points, you calculate y prime. And you draw a little line in the plane at the point you picked, representing the corresponding slope. Let's be more specific. We're going to look at y prime equals 3y over x, and I'll pick some points, and then I'll draw them in the plane. I'll draw the slope. For example, at the point minus 1, 1, so x is minus 1 and y is 1. So you plug those into the equation for y prime, and you get 3 over minus 1, or minus 3. I'll be very clear here. At the point minus 1, 1, the slope of the solution is minus 3. So what do? At that point, which was minus 1, 1, so I've drawn it here at minus 1, 1, you see it there, I draw a little line segment going down because its slope is negative. The slope is minus 3. Let's do another point. How about at 1, 0? So you plug in 1, 0 and you get 0 over 1, which is 0. So at 1, 0, the slope of the solution is 0. So here's what I've done. At 1, 0, it's over there, I've drawn a little horizontal line segment representing the slope being 0 there. And you keep doing this. Without a doubt, this is very tedious. For every point, you generate a slope. And then you go over to your graph, and at that point, you plot the slope. Ouch. To get a good picture, you spend days on this. Well, fortunately, slope fields, this process is built into graphing calculators now. It's amazing. And on computers. You have machines that will do this very quickly. They'll just take a point, plot the slope. Take another point, plot the slope. Boom, 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 boom. And in a second, you can get what we call a slope field, which might be 1,000 points with a slope at each point. That's amazing. My slope field in my picture only has 4 or 5 points. In a minute, I'll show you some pictures with more points. Okay. So I think we know now how to draw a slope field, and I hope we're convinced that it's something we don't want to do by hand. So let's try an example now, and we'll show some technology to draw a slope field. And I'll change the differential equation. How about y prime is 2x plus y? And you don't know the answer to this, do you? You do not know the function whose derivative is 2x plus y. We don't know the answer to that differential equation. That's good. It has a solution, but we don't know what it is. I don't care. I'm going to draw a picture of it, though. First, I'm going to draw a slope field, and then I'm going to use that slope field to find the particular solution that satisfies the initial condition that x equals 1 and y equals 1. In other words, the solution that passes through the point 1, 1. Okay, here we go. Normally, I would bring a computer in here and we'd draw the slope field, but we'll do a table of values just to sort of be a slow computer. What this table of values shows is the following. It has some x values along the top, and then it has some y values, and underneath is the calculation of the corresponding slope at that pair xy. For instance, when x is minus 2 and y is minus 1, if you feed that into the differential equation, 2x plus y, you get minus 4 minus 1 or minus 5. In other words, at the point minus 2 minus 1, the slope at that point is minus 5. Okay? You see how that works? And you fill in the table for a while, and then you can plot it. Well, I've used a computer here, and you see a slope field. This is a slope field. Your graphing calculator can do this. Let's check that result I just got. I said that at minus 2 minus 1, the slope was minus 5. In this graph, we're going from minus 2 to 2, and from minus 2 to 2 in the y direction. So at minus 2 minus 1, it's over there in the third quadrant. And notice the little tick mark, the little line segment is going downwards pretty steep because the slope is minus 5. It's got a negative slope and a fairly steep negative slope. So at least that point was correctly plotted. Now, I said this slope field shows a good view of the way the solution behaves. We want the solution through 1, 1. So here's what you do. Find 1, 1 on the graph. You see it there in the first quadrant, the little tick mark corresponding to 1, 1. And you start there with your pencil and you follow the tick marks because you're following the slope. So these tick marks tell you how to draw the solution. And you get a fairly decent representation of the solution, a solution that we haven't found. We never found the solution, but we've got a picture of it. Isn't that neat? That's how slope fields work. Let's practice. These are sort of advanced placement type problems. They kind of make us think about slope fields and what they're really talking about. Here will be the question. I'm going to give you 3 slope fields and 3 differential equations. And you match the slope field with the appropriate differential equation. So the differential equations are y prime equals x plus y prime equals x, and y prime equals y. 3 differential equations. We do not know their solutions, do we? But we'll still be able to figure out what their slope fields look like. Here are the 3 slope fields. Here's slope field A, slope field B, and slope field C. All right, I'm going to look at these a little bit closer. Notice that in the third differential equation, y prime equals y, if y is 0 in that equation, then the derivative is also 0, isn't it? Because y prime would equal 0. What that tells me is that when y is 0, now when is y 0? That's the x-axis. So along the x-axis, my slope field should have horizontal tick marks because the derivative is 0 along the x-axis. Does one of these slope fields have horizontal tick marks along the x-axis? This one doesn't. This one doesn't either. Uh-oh. Ah, this one does. So that's got to be the answer to the third one. Good. Let's do the same argument for the second one. Y prime equals x. That means if x is 0, the derivative is 0 there. And when is x 0? That's the y-axis. So along the y-axis, the tick marks should be horizontal. Let's see if any of my slope fields have horizontal tick marks on the y-axis. Look at the first one. Yep, there they are. The tick marks down the y-axis are horizontal. The second one, they aren't horizontal, and the third one either. So we now match the second equation with the first slope field. And the only one left is the first equation. That must match the, it will match B, the second slope field. Let's see why. Let's plug in a value. Suppose x is 1 and y is minus 1. At that point, the derivative is 0. So again, we should have a horizontal tangent at 1 minus 1. At 1 minus 1, the tick mark indeed is horizontal. So that's kind of a fun little puzzle. It requires some artistic talent, I think, to solve it. Good. Here's another kind of typical advanced placement problem where you play with slope fields. In this problem, you're given a slope field. There it is. It has tick marks going around in a circle, and then they get a bigger circle and a bigger circle like that. And they ask the following question. Given that slope field, which of the following functions could be a solution to the appropriate differential equation? So again, we're given that slope field. What's the solution to the differential equation that generated that slope field? Well, I hope you think, well, that looks like a bunch of concentric circles. And the fourth answer down here is a set of circles, isn't it? X squared plus y squared equals c squared. For every c value, you get a different circle, different radii. The first solution is a parabola. The second one is surely not a circle, and nor the third one. So indeed, the answer is the fourth equation. Good. Okay. We've seen some slope fields. We've seen how to verify that a given function is a solution to a differential equation. You're probably all saying, well, wait a minute. Let's get on to the real good stuff. How do you solve a differential equation? What are some of the techniques to find solutions? And the one technique we'll talk about now and use in the next lecture is called separation of variables. It's a fairly straightforward technique. I think you'll find it fairly easy to use. And this will permit us to solve a large class of differential equations, especially the ones that we need for the applications next lecture. So, as usual, I'd like to illustrate the technique with an example. Let's consider the differential equation dy dx equals y over x squared, and I'll put an initial condition on it, and that will permit me to determine the constant of integration. So my initial condition will be y of 1 equals 3. So I could draw a slope field for this, sure, but I want to actually solve the equation. I want to know what y is given its derivative. Well, here's how separation of variables work. It's exactly what it says. You separate the variables. You take all the people involved with y, all the y terms, and move them over to one side of the equation, and you take all the x terms and move them to the other side. In particular, dx goes over to the other side. We're sort of using a differential notation here. And the y goes down into the denominator on the left side. So now I have separated the variables. The y's are on one side and the x's are on the other side. Separation of variables only works if you can do this. In many equations, you can't separate variables. But this time we can. Now, I've got the variables separated. I can now integrate both sides of that equation. Okay, here we go. We're going to integrate both sides. What's the integral of 1 over y dy? That's the logarithm of the absolute value of y. How about the integral of 1 over x squared dx? Well, that's nothing more than minus 1 over x. And now both integrals have an arbitrary constant, don't they? There's one constant for the log part and one constant for the x part. Let's combine those arbitrary constants into one constant, and I'll call it C1. So you combine the two arbitrary constants into one. Okay, so I sort of have a solution. Log of the absolute value of y is minus 1 over x. Well, can we get y all by itself? Let's see if we can. Well, if I know the log of y, I could take e to both sides, and then the log and the e would cancel, so the left side would become just y, and the right side would be e to that power. So it's e to the power minus 1 over x plus c1. That's a big fat exponent. The exponent is minus 1 over x plus c1. And now I've got y all by itself, so that's a solution. But it's not a very pleasant way to write it. So let me show you some of the tricks they do in differential equations courses. We're going to use a property of exponents. You have e to a sum. It's e to the minus 1 over x plus c1. E to a sum is e to the first one times e to the second one. Remember, you add exponents when you combine with a like base. So that equals e to the minus 1 over x times e to the constant c1. Oh, good. Now, what is e to the c1? Well, it's a constant. It's our magic number e raised to an arbitrary constant. So it's a constant itself. I'm going to call that constant c. And so my better looking solution is y equals ce to the minus 1 over x. That's a better looking solution, isn't it? That's the general solution of the differential equation. Fairly awkward solution, but that's it. Now, how do you find the initial condition? Well, you plug in x equals 1 and y equals 3, and you get that 3 equals ce to the minus 1 over 1. X is 1 in the denominator there. And that's e to the minus 1. So I have 3 equals ce to the minus 1. E to the minus 1 is 1 over e. So if I multiply it through, c is 3e. So now I know the particular solution. It's y equals 3e times e to the minus 1 over x. Well, the back of the book won't write it that way either. They'll write it a different way. Again, we use some algebra. That e can move over with the other e, and it becomes 3e to the x minus 1 over x. If you take x minus 1 over x and split it up, you'll see that you end up with 3e times e to the minus 1 over x. So there's the final solution. Y equals 3e to the x minus 1 divided by x. And you probably have to say here that x is positive because you don't want to cross the bad point x equals 0. So we'll use x be positive here only. Whew, that was a hard problem. Separation of variables is pretty hard, especially in that case because I specifically picked a problem that had some pre-calculus issues that will come up in the following lecture. Some of these simplifications of the constant and some of the manipulation of exponents. So next time, our final lecture, we will use separation of variables. We will use these techniques for solving differential equations and look at a number of applications of differential equations. I think you'll really enjoy these applications because these are real-life problems. These are problems that reflect the usefulness of calculus in the world of engineering and science. So I look forward to our final lecture together. See you next time.